So we're going to begin chapter 2, which is about modeling distributions of data. This is section 2 on day 1. Today we're going to find and interpret the percentile of an individual value within a distribution of data. We're going to estimate percentiles and individual values using a cumulative relative frequency graph, and we're going to find and interpret standardized scores, or a z-score, of an individual value. Okay, first, percentiles. What is a percentile? Well, quite simply, it's the pth percentile. We have a formal definition, okay, of a distribution, okay, is the value with p% of observations below it. So if we say the 43rd percentile, that would mean that 43% of observations were below. Okay. Let's do an example and calculate some percentiles here. Wins in Major League Baseball. The stem plot below shows the number of wins for each of the 30 Major League Baseball teams in 2012. So our lowest was 55 wins, and the most was 98 wins up here. You notice they use a split stem. Okay, they use a split stem for everything except for the first one because it wasn't needed. Now it says find the percentile for the following teams: the Minnesota Twins, who won 66 games. Well, 66 games, that would be right here. That's 66. There are 1, 2, 3 teams below them. So 3 out of the 30 teams were below them. And that could, as a decimal, is 0.1, or 10 to the 10th percentile. 10% of teams were below the Minnesota Twins. B, the Washington Nationals, who won 98 games. Well, they were top. So isn't that the 100th percentile? Well, no, because you don't include them. You can never really have the 100th percentile. It's the 99th percentile is the highest you can go because you never really include yourself. So 98, there are 30 teams, and they were bigger than all but themselves. They were the largest ones, so they were bigger than 29 out of the 30 teams, which is 0.97. They were in the 97th percentile. So even though they were the top and nobody was above them, they're the 97th percentile. And C, the Texas Rangers and the Baltimore Orioles, who both won 93 games. 93 right here. Okay. So we can count all the ones below, but I'm just going to count the ones that are, if I count the ones below, I'd have to count all of these from this down. But I got 1, 2, 3, 4, 5, 6, 7, 8 of them that are not above that. So that means 22 out of 30 were below, which is about 0.73, or the 73rd percentile. Okay. Now, cumulative relative frequency really is just another way of saying percentile. Okay. It really is another way of saying percentile. It's a running percentage. We have what's called cumulative frequency, which we add up the counts. Okay. And then cumulative relative frequency is the percent from cumulative frequency. And like I said, this is just a fancy word for percentile. Cumulative relative frequency and percentile are really essentially the same thing. Let's look at this example then. State median household incomes. The table and cumulative relative frequency graph below show the distribution of of median household incomes for the 50 states and the District of Columbia in a recent year. And we're going to make the graph ourselves, but so we have frequency. So there was one state that had a median income between 35 and 40,000, 10 between 40 and 45, and so on and so forth. So the relative frequency, you can see 1 out of 51 is about 2%, 2% of the country. Now, cumulative frequency, well, it's still 1. And then cumulative relative frequency would still be 1 out of 51 is 0.02. Now, there were 10 between 40 and 45. So if we add that 10 to the one we already have, now there's 11. And then 11 out of 51 is 0.216. Now that's our percentile, about 22%. So about 22% were less than 45. About 22% were less than 45. Now we have 14 more. So 11 plus 14 is 25. So 25 out of 51 should be a little less than half, and indeed it's 0.49. So 49% of the observations were less than 50,000. Almost half of the states had a median income that was less than 50,000. 12 more between 50 and 55, so that'd be 37 for a cumulative frequency, and 37 out of 51, which amounts to 0.725 for our cumulative relative frequency. And then 5 more, so that'd be 42, and 42 out of 51 is 0.824. 6 more would be 48. 48 out of 51 would be 0.941, so 94th percentile there. 94% of the observations are below 65,000. And then 51 out of, and obviously 51 out of 51 would be 100. Okay. Which we never get to in percentile, but for cumulative relative frequency graph, it does help us to graph it. Okay, so now we're going to make this graph. We're going to start out, 35 was our low. There was nothing below that, so we have a dot here at 0. And graphing on this side here is the cumulative relative frequency, and then the median household income. So at 40, and less than 40, there was 1. We're here now. 40, and what's less than that is the 1 here. Well, that's about 0.02, which isn't very high, right about there. Might be 0.02, and we connect the dots here and connect them up. Then 45, we have to go back to this one. So we did this one. Now we're on this one, 0.216. So a little bit above, 0.2 is right here, a little bit above that, 0.216. 0.490 is 50,000. Well, that'd be 50,000 if there's half. It'd be right about here. 0.725 for, which is less than 55. 0.725, here's 0.7, 0.55 and 0.7, somewhere about here. 0.725. 0.824 for 60,000, so a little bit above 8 is here, and a little bit above that might be right about here. And 0.941 for 65. 94%, 0.94, well this is 0.9, we want to be above that, so about halfway, about there. And finally at the top here, leveled off a little bit, and there is our cumulative relative frequency graph. And it says interpret the meaning of the point 50, 0.49. Well, the point 50, 0.49, 50 is the median household income, and 0.49 is the cumulative relative frequency. So what that means is that 49% of states had median household income of less than $50,000. That's what it means. So let's say it again. I'm going to zoom out a little bit here. 49% of states had a median household income of less than 50,000. All right, now it says to use the cumulative relative frequency graph for state income data to answer these questions. At what percentile is California with a median household income of 57,445? Well, 57,445, here's 55 and here is 60. So 57,445 is almost exactly in the middle of those. And if we go up here, that's California, and then we come across, it looks like it's just under 80%. So maybe it's about maybe 79%. And we're estimating it. We don't expect it to be perfect. It's about 79%. And B says, estimate and interpret the first quartile. So they want Q1. Actually, we're going to do Q1, the median, and Q3. Well, we learned when we made box plots, when we did our 5-number summary, that 25% of the data is below Q1. In other words, this is the 25th percentile. That's what Q1 is. It's the 25th percentile. So if I go up here, 0.2, 0.25 would be right about here. If I come across to here and then down, ooh, it might be 46 or 40, about 46,000, we'll say. So about $46,000 is Q1. The median we can find the same way, except now this, of course, the median it's the 50th percentile. And if we go here, we come across with the 50th percentile. We kind of know what it's about going to be. Come on down. And let's say about 51. About 51,000. We know that the 49th percentile is 50,000, so it makes sense that the 50th percentile is a little higher than that. Q3 then is the 75th percentile. 75% of the observations are below Q3. And that turns out to be, when we look it up, about 56,000. Okay. Now, Z-score. A Z-score is a very important idea, actually, because it allows us to compare things that are not necessarily from the same data set. We can still compare them. It's also called the standardized score. You're going to hear that a lot too. Standardized score, Z-score, they mean the same thing. Okay? And whereas percentiles is almost always done with the median and the quartiles, the Z-score is a similar thing, but with a known mean and standard deviation. So these are both measures of location. We're measuring where does the observation lie in the data? Where does it lie? So now there's a formula, and one you should know. The Z-score equals the observation X minus the mean divided by the standard deviation. And you'll get to know that one very well because it's a very important one. So let's look at an example. Wins in Major League Baseball again. In 2012, the mean number of wins for teams in Major League Baseball was 81, with a standard deviation of 11.9 wins. Well, find and interpret the Z-scores for the following teams. The New York Yankees with 95 wins. Well, we would do 95 minus the mean, which is 81, divided by 11.9, which would be 14 over 11.9, which turns out to be 1.18. And we have to interpret that. But what that means is that the Yankees were 1.18 standard deviations above the mean number of wins. And then for the New York Mets, they had 74 wins. So 74 minus 81, the mean, divided by 11.9, the standard deviation, which is -7 over 11.9, or -0.59. Now, if we get a negative z-score, that means our observation was below the mean. A positive z-score means the observation was above the mean. So let's look at that one. This one's going to be very similar to what the Yankees were 1.18 standard deviations above the mean. The Mets were 0.59 standard deviations below the mean number of wins. Okay. So, and another example of how we can use this, we'll do with these the home runs here. Home run kings, we'll do that in a second. But that's how we calculate z-score, and that's what it means. All right, so let's look. Home run king. Okay. Babe Ruth was the first home run king. He had 60 home runs. And then Roger Maris had 61, Mark McGwire had 70, and finally Barry Bonds had 73. So what if we wanted to compare those over time, and we said in Babe Ruth's year, the average player had 7.2 home runs when he had 60 home runs, with a standard deviation of 9.7. In 1961, when Roger Maris hit 61 home runs, the average was 18.8 home runs per player, with a standard deviation of 13.4. So if we want to compare those, we can do a z-score for each player. For Babe Ruth, the z-score would be 60 minus 7.2 divided by 9.7, which is 5.44. In other words, Babe Ruth was 5.44 standard deviations above the mean. Now, Roger Maris, his z-score was 61 minus 18.8 divided by 13.4, which turns out to be 3.15. So not even close to Babe Ruth. He may have hit more home runs in a year, but Babe Ruth, compared to his peers, did a better job. Babe Ruth was far above Maris in that respect. Now McGwire, his z-score would be 70 minus 20.7 divided by 12.7, which is 3.88. So he was 3.88 standard deviations above the mean. Better than Maris, but not even close to Babe Ruth still. And finally, Barry Bonds. His z-score would be 73 minus 21.4 divided by 13.2, which is 3.91. Again, better than Maris and McGwire, but not even close to Babe Ruth. So some would argue that Babe Ruth is still the home run king because he did so much better in a time where fewer home runs were hit. He hit 60.